This is question number 19 in chapter 19. It says, consider the network of resistors shown in the figure 19-40. Answer qualitatively. A, what happens to the voltage across each resistor when the switch is closed? What happens to the current through each when the switch is closed? And C, what happens to the power output of the battery when the switch is closed? Let's start with A, B, and C. Here we've got the switch. Specifically the only switch in the circuit here, and when it's closed, that admits current through R2. It effectively adds a resistor in parallel, and as I add resistors in parallel, that lowers the net resistance or the equivalent resistance of this parallel network. So by lowering the resistance of the network, by adding a resistor, as awkward as that is to say, conversely, by the way, remember that adding resistors in series increases their resistive value. Adding R2 in this case by closing the switch lowers the equivalent resistance of the network. And therefore, since R1 doesn't change, it lowers the total resistance of the entire circuit. So therefore, the current flowing through the resistor R1, so here total current flowing out of the battery through R1, it's going to increase because of the reduction in the total current, the reduction in the total resistance of the combined series parallel network. The current flowing through resistor 2 also increases because, hey, it used to be 0 because the switch was open and now it's closed, so it goes up. However, the current flowing through the other resistors, R3 and R4, will actually go in the opposite direction. We'll answer that question in just a bit as to why that's true. But first, let's take a look at V1. The voltage across R1 increases because we've increased the current flowing through it. Its resistance value doesn't change. V equals IR. This is Ohm's law. So I can say then if the current increases, and therefore the voltage will increase. So that goes up. Because I'm dropping more voltage across resistor R1 now, and my battery voltage does not change, that means that between these nodes, I'll call them A and B, the voltage drop across all of those resistors in the parallel network goes down. The loop law shows that more voltage is now dropped across R1, therefore less voltage dropped across R2. So the voltage dropped across R2 will go down. Now, previously the switch was open, so technically speaking, the voltage drop between A and B was has gone down, but the voltage, there was no current flowing through the resistor R2, and now there is. So let me go ahead and revise that. Therefore, since there was no current flowing through there, and now there is, the voltage drop has technically increased. However, when I look at voltage dropped across R3 and R4, it's gone down from what it used to be. Those have gone in the downward direction because I've dropped more across R1, and therefore there's less based on a single loop that I would draw, perhaps like this one, this dashed line that I'll draw. If this is the loop that I'm going to look at, there's less voltage dropped across R3, and therefore it goes down, and for the same reason, the voltage dropped across R4 goes down. For those using Ohm's law, we'll show you then if the voltage goes down, the resistance doesn't change, then the currents through those branches 3 and 4 goes down as well. Part C is looking at power. Power is equal to the total current in the network times the voltage. The voltage of the battery doesn't change, but the total current does increase, and therefore we can say that the power increases as well. For the reason that current has increased. Part D goes on to then make some additional, give you some additional information. It says, let R1, R2, R3, and R4 all equal 125 ohms, and the voltage of the battery is now 22 volts. So they've assigned some numerical values to these to the battery and these resistors. So all of the resistors are 125 ohms. Okay, so now we have to tackle this problem. Switch 1 is originally, let's see, in part D they say, determine the current through each resistor before and after closing the switch. So let's start before closing the switch. Before we close the switch, resistor R2 is not part of the circuit. The switch is open, no current flows through the branch from node A to B. So we really have a parallel legs with resistors R3 and R4. So what I'm going to do first is find the total resistance in the circuit when switch 1 is open. So therefore, I'm going to say it's going to be 125 ohms, which is the resistive value of R1. But then I have to add to it the equivalent resistance of R3 and R4 together. So let's go ahead and do that. Let's see here. R3 and R4, that's going to give me, well, one way to solve it would be to say, okay, well, the equivalent resistance is 1 over Req is equal to 1 over 125 plus 1 over 125. That's the value for the R3 and R4. That gives me 1 over Req is equal to 2 over 125. And now I can basically take the inverse of that, 125 over 2, and place it in this equation. So the total resistance of my network is 125 ohms plus 2 over 125. I'm sorry, I wrote that incorrectly. That's 125 over 2. So I need to take the inverse of that. So 125 ohms over 2. And when I do that, I'm going to get 187.5 ohms as the total resistance now in the circuit when the switch is open. I can now figure out the current flowing out of the battery. The current flowing out of the battery is the total voltage, 22 volts, divided by my total resistance that I just found, 187.5. And I'm going to get basically 117.3 milliamps, or 0.1173 amps. So there's the current flowing out of the battery. That also happens to be the current flowing across resistor R1. So now I can use Ohm's law locally at component number 1. So I'll say V1 is equal to the current, total current, times R1. And I'm going to multiply 0.1173 amps times 125 ohms, and I get 14.66 volts. So there's the voltage dropped across resistor R1. Using the loop law, let's go ahead and use the dashed blue line here that I drew earlier. I know that 14.66 volts are dropped when across R1 when the switch is open. So therefore, the balance of that, 22 minus 14.66, or 7.34 volts, is going to be dropped across R3 and R4. So 17.34 volts dropped across, I'm sorry, 7.34, my mistake, 7.34 volts dropped across R3 and R4. Let me go ahead and write that here. So the voltage dropped across 3 is equal to the voltage dropped across 4, which is 7.34 volts. So the current through each of the resistors can be found using Ohm's law. So I'll just find the current flowing through resistor 3, and I'll say that it's going to be the voltage dropped across resistor 3 over the 125 ohms that all the resistors have that value, and I'm going to get 0.0587, 0.0587 amps. That's the current flowing through resistor 3. So I can also say then that the current flowing through resistor 4 is going to be the exact same thing because I have the same voltage and the same resistance. So I get 0.0587 amps. And you'll notice that these are each exactly half of my total current of 0.1173 amps. So when I take a look at this total current, it's divided equally between resistors 3 and the currents flowing through branches 3 and 4 respectively. Okay, so then the switch now is closed, and so now that we're going to do this whole business all over again. Now that we've added resistor R2, our approach will be very similar. So I'll say that the total resistance in the circuit is going to be the 125 ohms from resistor R1 right here, and then I'm going to likewise end up having something that looks like this, 125 over 3. And when I do that, I'm going to get a total resistance of 166.7. Notice that the resistance has gone down after adding that resistor. This expression right here that I've placed the asterisk next to comes from something similarly that I did over here at the beginning. I'm just not going to redo it. So now that I have the total resistance, I'll find the total current. The total current is the total voltage, 22 volts, divided by the value that I just found, 166.7. And I end up getting, for the total current, 0.132 amps, 0.132 amps. So that's the current flowing through resistor 1. So it's not only the total current, but it's the current flowing through that first resistor. I now need to figure out the voltage dropped across resistor 1 with the switch closed, and the voltage dropped across resistor 1 is going to be the current flowing through 1 times the resistance of 1, or 0.132 amps times 125 ohms. I'm going to get 16.5 volts. So now with the switch closed, I have more voltage dropped across resistor R1. This was anticipated, as we saw here in the early parts of this problem. And that means that there's only 5.5 volts to be dropped across 2, 3, and 4. The balance of the 22. So 22 minus 16.5 yields 5.5 volts dropped there. Finally, the current flowing through one of those remaining resistors I can find by saying, let's go ahead and take a look at 2. The current flowing through 2 is the voltage dropped across 2 divided by the resistance value of 2, or the 5.5 volts over the 125 ohms. It's going to yield a very small branch current of 44 milliamps, or 0.044 amps flowing through 2. And likewise, I can see that's now 1/3 of the total current because these resistors are 2, 3, and 4 are all exactly the same. The current basically breaks into equal thirds. So I have 0.044 amps flowing through all of them. So we can see that the values that we found in parts D here and then the second part of D in these sections here are consistent with what we saw in A and B.